Okay, this is take two on this because devastatingly I did not screen capture the first time, but this is just meant to be a little supplemental lecture um, to kind of talk more about wave functions and orbitals and some of the stuff we talked about quickly today. So I want to harken back to that idea that these electrons behave as standing waves. And so I first want to just talk about what is a standing wave and how do we think about those. And to me, I always think about these in the context of string instruments. Like I said, I played violin for like 15 years. But probably something like a harp is an easy way to think about this. And on a harp, we have a lot of different strings here. We've got this long string at the end and a short string at the top. And at either end of those strings, those are fixed. And so if I just draw, kind of what these look like, I've got my long red string, and I've got my short blue string. And when I pluck these strings, they make a sound because the string vibrates back and forth. And we intuitively can know that the longer string is going to have a lower sound, a lower tone to it, and the shorter string will have a higher pitch tone to it. And the reason for this is directly related to the properties of the standing waves that these strings are able to hold. So a standing wave is a kind of wave where there are fixed points on the wave that where it's kind of locked into this configuration where it's held at either end, as opposed to a traveling wave where if I say I had a rope and I put a wave into it, and then at some point later in the future, it's gone and it's going like this, and then later it's, at the end, that would be a traveling wave. A standing wave is something where we have oscillation back and forth. So we've got this kind of oscillation between this, and then at some point in the future, the wave is flipped downwards. It's vibrating back and forth between these two positions. And similarly for my blue one, it's going to be vibrating back and forth between these two positions. And so with these kind of standing waves, we can think about a few things here. First off, we can think about how we know intuitively that the pitch of this red wave is going to be lower than the pitch of the blue wave. And we can relate that to some properties of these waves. So we know that a wave, the curve for a wave looks like a sine curve. So a regular wave looks like this, and the wavelength of that wave corresponds to the full sine curve there, and that's what we call lambda. So in each of these cases for my harp, what I've drawn here is 1/2 of that wavelength, right? Because if I were, for example, to continue my blue one, I would have to draw the other half of that full sine curve. And so that's saying that this distance is equal to lambda over 2. And the same thing for the red one, this distance is equal to lambda over 2. Now, there's also the concept, and lambda in this case is wavelength, there's also the concept of frequency. So lambda equals wavelength. This nu is equal to frequency. And frequency is inversely proportional to lambda. So lambda is proportional to 1 over frequency, which means that our red wave here has a long lambda and will therefore have a low frequency, whereas the blue wave has a relatively short lambda and will therefore have a high frequency. And energy is generally proportional to frequency. So in this case, we have that, like I said, energy proportional to frequency. So we have the energy of the short wave is going to be greater than the energy of the longer string. And this matches our understanding of, the tones of these two strings. The lower pitched tone is lower in energy. The higher pitched tone is higher in energy. And so what I want to connect this to on the harp is what determines the energies of these two strings when plucked is the wavelength and everything. But what it ultimately comes down to is the position of these fixed points on the wave, because this wave can oscillate up and down, and this other, the portion that we don't see oscillates up and down. But this point at the beginning and this point at the middle never change, right? They are always going to be at 0, whereas even if as the string passes to the bottom, that point is still fixed because it's literally fixed in place by the fixtures on this harp. And so as far as the standing wave of these strings are, this is a node. A node is a place where the wave is fixed at 0. And so we have nodes, in this case, on either end of our standing waves, because these are the lowest possible. This is what we get when we pluck the string. This is the longest wavelength possible that we can get where we have nodes at either end. Now, one cool thing about standing waves and the nodes that these have is that it necessarily means that we have quantized energy levels. Because we know that energy is related to this wavelength here, we can't just have any wavelength for a given set of nodes. So for example, let's say I have these two nodes at this distance. If I had a wave that had, this wavelength, where this was my wavelength, this wavelength is not compatible with this distance of two nodes here, the distance between this node and this node, because that would mean my string is not fixed here. It's not at 0, and so it would be unattached on my actual harp. So the only wavelengths that are compatible with this node pattern are ones where it's either lambda over, it has to be some multiple of lambda over 2. So this is no good. This does not work. And so the energies of standing waves are quantized as a result of this, meaning they can only have specific discrete values. They cannot have continuous values. So this is the case that we showed here is in both cases, the waves I drew have, in both the red and the blue cases, these have wavelengths of lambda over 2. But as I said, the wavelength just has to have a value of some multiple of lambda over 2. For example, it does work. I'm running out of space now, but if I were to draw down here, I could have that. I could also have this. That works. In this case, the distance between these 2 points is equal to lambda. I could also have 3 over 2 lambda, which would look like this. That would also work. So while they are quantized, it doesn't mean there is only one value available. There can be multiple values. And these higher, these shorter wavelengths that are possible, that are also commensurate with my node patterns, these are what we'd call harmonics. And so I'm showing this here. You can see this if you want to type in this video, pause the video, type in this thing. You can go to YouTube and watch this video of these two people holding this spring or string or something, where we have a very similar situation. Imagine that the hands of these two people are my nodes, and the lowest energy level, the lowest amount of energy they can put into this, where they create a standing wave, creates this wave that oscillates back and forth. just like the one we drew before. But if they work a little harder, they can create a wave that has my distance here is lambda over 2, wavelength over 2. But if they work a little harder, they can create a situation where the distance is equal to lambda. And because energy is proportional to frequency, it's also inversely proportional to wavelength. And so shortening the wavelength here, because we've gone from this being half the wavelength to this being the entire wavelength, means we've also increased the energy. So going from here to here is an increase in energy. And in addition to shortening the wavelength, one more thing, and that's really the big point I want to make here, the point to observe is we've added an additional node to this wave, where as this wave, if you watch the video, you'll see oscillates back and forth. It's gonna, this section is gonna oscillate such that it faces that way. This section is gonna oscillate such that it goes that way. These two sides will be out of phase with each other, but there will be a point right in the middle that stays fixed at 0. And so that point that's fixed at 0 is a new node that has been added to the wave function of this standing wave that's in this string or spring or whatever. And so increases in energy when the energy of a standing wave increases, we increase the number of nodes. Or one way of doing that is to increase the number of nodes. Another way to do that is just to shorten the distance between nodes, but we'll see when we get to atoms, we don't really have this these endpoints to worry about. So the only way to increase the energy of, or the most direct way to increase the energy of electrons in atoms is by adding nodes. Okay, so how do we now think about this in the context of a 1s orbital? Well, we've always drawn 1s orbitals like circles. And as I mentioned in class, this kind of picture can be a little misleading, though it is what we will do quite a bit. But it can be a little misleading because it doesn't quite give us a real picture of everything that's going on inside the orbital. So first off, let's remember a couple of things. Let's remember that this is an orbital in a three-dimensional space where we've got an x, a y, and z axes. And if we were to just look at what this actual function looks like, so I'm going to call this 1s. If we were to just look at what this function looks like along, let's say, starting from the nucleus and going along the x-axis, we can plot that function where we plot on the y-axis the magnitude of the wave function. And on the x-axis, we just plot the radius in terms of distance from the nucleus along x. And if we were to plot this, what we would see is that the 1s function is very large. In fact, it goes towards infinity at the nucleus. So backing up here, at 0, this is the nucleus. And then as we get further and further away, we're getting further from that nucleus. So near the nucleus, the wave function is very large. It drops off exponentially and approaches but never crosses 0. Approaches 0. So one thing that is misleading about this picture above is that it makes it seem like there is some sort of horizon to a 1s orbital, when in fact we see that the function just sort of gradually decreases over time. Now, the reason we do that is because it's very hard to draw something that decreases over time. So we sort of get around that by saying, well, if once the psi1s function gets below a certain level, let's say it gets, I'll just say this is the point I'm cutting it off, then I pretend that's my horizon. And so it's like, okay, everything within that, after that point, I'm just going to pretend is outside, even though there's actually some very small amount of wave function there. The other way that I talked about in lecture that we can draw these is by doing these kind of density plots where we show, okay, here's my nucleus in the middle. And then we use kind of the density of little dots as a way to show what the relative magnitude of the wave function is. And so we know that it's largest near the nucleus and then it tails off. So if I were to do this by showing with the magnitude of dots, I would have lots of dots near my nucleus. And then it would gradually decrease the further out we go as this function gets smaller and smaller. What's nice about this picture is that it doesn't have to worry about that problem of, oh, it just approaches zero, but actually never crosses zero, and yet I'm still drawing some kind of boundary to it because we're not actually drawing a boundary. However, it's kind of annoying to draw. So most of the time we'll just draw these pictures where, but I want you to just remember that that boundary is fake and that these wave functions extend and only approach zero. What I also want to recall is that the 1s function is spherical. It is spherically symmetric. And so we arbitrarily chose to look along the x-axis here. But if I were to look along, start at the center of the nucleus and go in any direction, we would see this similar thing. So like I drew in class, I think I drew like this, where here's x, y, z. And we said, well, you can see here's what the function looks like along x. Exact same picture we drew here. But we could also go along negative x. We could go along the y-axis coming out at us. We could go along the y-axis going away from us. We could even go, along z, whatever. All these directions, any way we go, this function is going to be decreasing. And it is, no matter which direction we're pointed, it is highest near the nucleus and then gradually decays. And remember here, actually, maybe this picture is a little misleading too. This is not to say that the function is maximized along z and along these axes. I'm just saying, as I go along the y-axis, here my z is actually not really, not really it's z. It's more like this is my psi1s axis. So it's just saying that in the x and y directions, the function is the same in any direction. Okay, so there's our 1s orbital. This is the lowest energy possible orbital because it corresponds to all of the wave function is in phase with itself, right? We don't have any nodes in our orbital, and we know that nodes correspond to an increase in energy. So we can achieve higher allowed energy states within this quantized system by adding nodes to these orbitals. Now, there's a couple differences between the ways that nodes are added for a string and the way that they're added for an orbital. First off, orbitals, we don't have fixed points that the electron is connected to at either end, like we do here. And so we're not so much worried about that as a boundary condition. We also have a three-dimensional thing rather than a one-dimensional thing. So the way we add orbitals is going to be, or the way we add nodes is going to be a little different. So there's essentially two ways to add nodes to an orbital in a way that raises its energy. So if we increase the energy of an orbital, one of those ways is to add what you can think of as what's called a angular or a radial node. And so set of axes. and let's say just X and Y, we're just looking from the top right now. A radial node is a node that occurs at a fixed distance from the nucleus. So here's my nucleus in the middle. Radial node has a radial node is at a fixed distance from the nucleus, right? So here's my nucleus. Distance to the node here is the same as there, is the same as there, same everywhere. Now, what this means is that the function is changing sign as I cross that node. That is a place where the function is fixed to be 0 everywhere along this node. And on opposite sides of the node, the wave function is out of phase with one another. So as I cross the node, my sign has to change, and it has to go from positive to negative or vice versa. So that means within my, I'll arbitrarily say that inside this node, I'll color that red, say that red corresponds to positive. Actually, it doesn't even matter. I'm just going to leave it ambiguous because it doesn't really matter one way or another. And then outside, my function is negative, or the opposite sign of whatever it is inside. Now, one thing, I think I was trying to think about analogies for this. One analogy you could have for this, and if this doesn't make any sense, don't worry about it, because maybe it's a bad one. But you know those parachutes that everybody played with as a kid, where it's like, here's my parachute, and you got a bunch of people holding on to it like this, right? If everybody who's holding on to this parachute, if we're all in sync, kind of raising it up and down, right? We're lifting it up and down. We could generate a standing wave in this parachute where it's kind of going all up and then all down and all up and all down, the whole parachute moving as one. Now, probably you couldn't do this as a kid because we were all weak and have tiny arms, but if you were to add enough energy to this parachute, you could generate a form of it where part of it is going up here, and then the other part is coming down. And how do I draw this? Where you generate a harmonic, that's essentially the two-dimensional equivalent of this picture, where the center of this would be moving upwards. While the outsides of the parachute are moving down. And you could have it kind of oscillating with back and forth in that way. That is essentially the two-dimensional analog to our 2s orbital, where we have opposite signs going back and forth in this three-dimensional orbital between the nucleus, and then we have some radial node at a fixed distance from the middle before we cross the sign. So if I do the same thing for this, if that didn't make any sense, you can tune back in, and I'll not talk about it again. We do the same thing where we look just along the x-axis and plot our wave function versus r. This is now side 2s at the nucleus. At the nucleus, the wave function is positive and large. We'll call red arbitrarily positive and blue arbitrarily negative. And then at this fixed distance where I have my radial node, I don't like how that pencil writes, it's hard to read. Where I have my radial node, the function changes sign to becoming negative and then gradually decays back towards 0. So there is a point here where my function is fixed at 0, and that is my radial node. And this function looks the same because the 2s orbital is spherically symmetric no matter which direction I process in. Whichever direction this r vector is pointed, whatever direction I look along, my 2s function is going to look the same. And generally, the picture we draw of a 2s orbital is not typically looks like this. It's more commonly we draw something like that, where again, we've kind of arbitrarily chosen a point and said, well, that's, as far out as we care to draw it. So adding a radial node, this is radial nodes occur at fixed distance. And importantly, where r is not equal to 0, right? Here's my radial node. R is not equal to 0. Another way of adding a node is what's called an angular node. And this is what we see in a 2p orbital. So again, just going to draw axes, X and Y. An angular node is a nodal plane, which say it's in the YZ plane, but we'll just say, because I'm just looking in XY, it only is XY. Really, this is plane. Looks like this. It can be used coming out this way, but we're just gonna worry about the two-dimensional picture for now. So I'm gonna undo that. And in this case, we've got our function looking like, I think this works. Our function looking like this on one side. And this on the other side, where the two sides of this plane are out of phase with one another. And so they are very much oscillating, just like this one-dimensional picture is, but they just also extend into into 3D space. This corresponds to our 2p orbital, which we have typically, we typically draw with that dumbbell shape. We shade one side of it to say it's negative, but again, this just has an angular node pointed down the middle of it. So angular node, and that angular node is what defines the shape of this orbital. So what's different about an angular node is it passes through the nucleus of the atom. Remember, with radial nodes, radial node is at a fixed distance, r unequal to 0. And the angular node is not spherically symmetric. So if I were to do the same thing and graph psi 2p versus r along x, I would see psi 2p start large and then gradually, oh, actually, I'm lying. What I would see is psi 2p, and actually I'm going to draw it a little differently. Sorry. So I'm going to draw both sides. Let's start. We'll go both ways. So we'll show here's 0, here's psi 2p. At r equals 0, I'm going to call these x and minus x. At r equals 0, our function is fixed to be 0 because we have a node right here. Right? We're here right now, so we're at a node. And that means when we go to the right, our function is going to go up. and then it's going to slowly decay back towards 0. On the left side, it's out of phase. It's going to go down and slowly decay back towards 0. So again, this picture looks a lot like our wave here, just without the nodes, the fixed points at either end, just decays out to infinity. A difference with this is that, like I said, the node now is at 0, at our nucleus, which is different than being at some fixed distance from the nucleus, like the radial node. And this node is, this wave function is no longer symmetric in all directions, because if I were to take instead the picture, let's say I go along this node here, what would I see? So if I'm going now from y to negative y, and I wanted to plot psi 2p, well, everywhere along the y-axis, my function is 0. So I would just see this. I see nothing. I'm just going along the node. Now, interesting question, but it's a little beyond the scope of what we're necessarily going to talk about, would be what would we see if we went at some weird angle, like this. Turns out that it basically looks the same. It's just smaller. So be like this and this. And this is why the p orbital is drawn the shape that it is, because directly along that axis is the maximum magnitude, right? And as we go off that axis, the magnitude gets smaller. But that's a little besides the point. The point that I mainly want to make here is that the second way of coming to a increased allowed quantized orbital level is by adding an angular node to this orbital. So we could either add a radial node or an angular node. Now, there's nothing that says these are the two most simple ways to add orbitals, right? 2s and 2p orbital. There's nothing that says we can't do more than that. And in fact, we do plenty more than that. What if, for example, we want a 3p orbital? A 3p orbital is made by the combination of an angular node and a radial node. So x, y. Now I'm going to draw my nodes. So a 3p orbital has both an angular node as well as a radial node. Otherwise, all the same rules still apply. Whenever we cross a node has to be 0 in our wave function. Whenever we cross a node, we have to change the sign of our function. So let's say I'm like this on this side, and that means I like how this pencil looks. I think that works. That means I'm opposite on the other side. And then that means when I cross this radial node out here, right, inside the radial node, this just looks exactly like a p orbital. And then I get to a point where, I hit this radial node. Now I have to flip again. So I'm going to have my function changes sign. And similarly on the other side here, we've got this, and it's going to change sign outside as well. And commonly in 111, we would have you draw this orbital as, we would say, well, here's one lobe, there's another lobe, and then it's got this larger lobe, and here's my, my nodes are like this and like this. So it still has that, sort of dumbbell shape associated with the p orbital, but we've added this radial node in as well. And again, one thing that you should try for yourself is plot. What does this function look like as I go from here along the x-axis and the other way along the x-axis? So setting it up for you, you're going to plot psi 3p. I have a node at the center. I've also got nodes in the positive x and negative x directions. This one at the center is my angular node. These two that I'm seeing out here, my two radial nodes. Or it's one radial node, but it's crossing this line at this x-axis at two different places. And so what does that function look like? And I'll draw it in a second, but I would highly encourage you to pause the video, quickly try and draw it yourself and see if you agree. So what that will look like is we're fixed at 0 at the central angular node. Then red is positive, so we're going to go up. Then we cross this node, decay back to 0. On the other side, we crossed a node, we crossed the middle angular node, so we're going to be negative. Then we're going to cross again and decay back to 0. So something like this, at least qualitatively, captures the positive and negative behavior of our orbital. So hopefully that is what you had as well. Okay, so knowing about these nodes, the angular and radial nodes, gives us a lot of information about the energy as well as the shape of the orbitals. And so I wanted to spend a lot of time reviewing this because it is going to be crucial as we get into a lot of MO theory and things like that, to just have in your mind, what is the shapes, especially of these orbitals? And that's intimately tied to the nodes, and particularly the number of angular nodes. We're gonna care less about radial nodes down the line, but for now it's worth considering both. So the total number of nodes in an orbital is equal to n minus 1. So if I have a 2p orbital, we have a total of 2 minus 1 equals 1 node. If I have a 4d orbital, we've got a total of 4 minus 1, or 3 nodes. Now the number of, and n being my principal quantum number, which is this number out front of the orbital, 2p, 4d, 2 is my principal quantum number, 4 is my principal quantum number here. Now the number of angular nodes is going to, that's equal to L, the angular momentum quantum number. Nice how those two things align, angular momentum, angular nodes. And then by math, we know the total number of nodes is n minus 1. Nodes are either angular or radial. So if the total number is n minus 1, then the total number of radial nodes is number of total nodes minus number of angular nodes. So n minus 1 minus L, commonly written as n minus L minus 1. To determine the number of angular nodes, that depends on this L. So recall that when L equals 0, we have an s orbital. When L equals 1, we have a p orbital. L equals 2, d orbital. L equals 3, f orbital. So in a 2p orbital, L is equal to 1. And so if we have one node in a 2p orbital and L is equal to 1, then we have, this means this must be one angular node. In a 4d orbital, L is equal to 2. So this means we must have 2 angular nodes, and then by process of elimination, we have one radial node. And we can do this to come up with the, the way that the nodes look for almost any orbital, especially SP or D, just based on knowing how many there are. So even if I think, oh, a 4D orbital, that's hard to figure out. Well, we know that it has 2 angular nodes and 1 radial node. And so we're getting a little ahead, but you might remember that if we could think about, well, let's say we have, here's my axes, X, Y. If I have two angular nodes, let's say those are pointed along the X and Y axes. Those are planes in the XZ and the YZ plane. And then I've got one radial node that happens at a fixed distance. Then I can use the exact same approach that I did before. I'm gonna fill this in, where I just make sure the sign is changing across every one of these nodes. And this picture is the same as, you know, the picture we've maybe drawn before of a 4D orbital that would have this cloverleaf shape. Where it's got two angular nodes and one radial node. So by figuring out how many nodes we have, we can draw just about any orbital and know what the signs of those functions are. I could take any direction starting at the nucleus, go along this direction and say, what does the function look like? And I could basically get a sense of, oh, it's positive, and then it goes back to 0, and then it crosses negative, and then it decays back towards 0, but doesn't cross it again. Okay, so we did all this because I wanted to build up towards what's called the radial distribution function. And one thing we don't do in 111 is kind of draw these functions like we did here. And we have to be able to draw those to think about the radial distribution function, which has a strong impact on some properties that are relevant to inorganic chemistry. So I want to draw a couple things here. First off, we're going to go back to the 1s orbital, which, as we recall, has a wave function that decreases like this. So here's psi 1s decreases like that. Now, what the radial distribution function is trying to answer is, what is the probability of finding an electron at some distance r from the nucleus? So we need to think about two things. We need to think about probability, and we need to think about what it means to be at a distance r from the nucleus. Now, we know that the wave function tells us the properties of that wave, but that what tells us about probability is actually the wave function squared, right? That's that probability distribution. And for the 1s function, it looks pretty similar. I mean, you square something that's positive everywhere, it's positive everywhere, and it still looks pretty exponential decay-like. So I'm going to graph that over here bigger. So that's my probability distribution. Now, the probability distribution is the probability of finding an electron at some exact location, some point. So if my atom is here, and I want to say, well, what's the chance of finding an electron right here? That's what the probability distribution can tell me. But that's not the question I'm asking. I'm asking, what's the chance of finding an electron anywhere at this distance where say this is a distance r from the nucleus. I don't care whether it's here or here or here or here, anywhere along this distance. And in fact, this is a in 3 dimensions, this is a shell that has at this distance r. And so to answer that question, we also have to consider that the surface area of this shell, how many points there are on this shell, is going to affect the probability, right? Because if I have two different, if I'm considering 2 different r's, and one of them is smaller, this shell has significantly smaller surface area than this shell. And so if there was the same probability of finding the electron at any point on either shell, well, you'd say, well, it's much more likely to find it somewhere on this shell because there's just so many more points on that shell than there are on this one. And so we need to capture that behavior. And it turns out that the surface area of this shell scales as a function of r squared. So, and I'll write this in blue. Surface, I'll do SA. SA is proportional to r squared. So if I double the radius that I'm going out, I get 4 times the surface area. And so I can plot that r squared now on my picture on the left. If r is 0, then obviously r squared is also 0. So it starts at 0, and then it increases looking like r squared. So now what I really, really care about is the combination of these 2 things. So what I'm going to do is I'm going to take psi 1s squared, the probability distribution, and I'm going to multiply that times r squared. And what that gives me is something I call, not me, but that everybody, is something called the radial distribution function. I'm going to call that capital R squared. And so you can just see qualitatively, we're going to do a lot of qualitative math in this class, very little quantitative math. At distance 0, so this is always label your own. At distance 0, r the r squared is 0. Wave function is large, but something large times 0 is still 0. Then both of these functions are going to be positive, and then the psi squared dies off exponentially while r increases at a factor of r squared. Turns out psi squared dies off faster than r squared increases. So well, first let me draw. So we're going to increase. Then the red function dies off faster than the blue function grows in. So that causes us to take a turn and go back towards 0. And so this function is my r squared. And what's nice about this is it tells me very clearly, oh, there's some point here where you are most likely to find an electron at some distance from the nucleus. So the peak of this radial distribution function tells me that there is a single distance from the nucleus that I am most likely to find that electron. Okay, so last thing I'm going to do here is just talk about the radial distribution function for a 2s orbital. It's going to be very similar. The only difference between these 2 things is that our wave function is different. So rather than having a wave function that is positive everywhere and just decreases, so psi 2s now is positive there, then goes negative and approaches back to 0. This means that my psi 2s squared, because a negative number squared is going to be positive, 0 squared is 0, positive squared is positive. So it's going to look like positive, comes down, touches 0, then comes back, and then approaches 0. So now when I draw my same picture I drew before, R0, here's my psi 2s squared. That's my wave function. My r squared still looks the same. R squared. And now when I multiply these two things together, I'm going to get something interesting happening, which is I've got two locations where the function's got to be zero, because here r squared is zero, so that's got to be zero. And here psi squared is zero, so that's got to be zero. So what I end up getting is something that looks like this. Okay, let's draw it a little better. Something like that. You know, these aren't necessarily to scale at all relative to each other, but the qualitative picture is what we're looking for, which is interesting because what this says is there are multiple maxima to this function. So the 2s orbital has a maximum probability, the location, the electron is maximally likely to be found at some location that's pretty close to the nucleus. This is a local maxima. I don't know which of these is actually larger in the actual function. They're not the same. I know they kind of look the same here. But it has some peak where it's pretty likely to find the electron pretty close to the nucleus, then less likely, and then more likely again. And that's, you know, that matches our intuition from drawing a 2s orbital, where it's like likely to find it in here, then there's a node, and then it's likely again. But the radial distribution function actually quantifies that to a degree. And this is going to be very important when we talk about shielding, which I hope to do on Friday. Okay, so hopefully this was helpful in terms of thinking about wave functions and orbitals.